Gaussian bosonic communications and information theory. Today, I want to tell you first just a couple of things that dropped off the end of the talk yesterday, and then I want to tell you just a collection of some things that we know a little bit about but don't know a lot about, or some open problems. Okay, so day 5, a little bit of quantum correlation still, and some open problems. Okay, so the first thing I wanted to do was at the end of lecture yesterday, I mentioned that for this attenuation channel that has some transmissivity lambda here and some vacuum state only that comes in here. So we have our input that rings off a beam splitter. I told you we could compute the quantum capacity of this thing. And it depends on the amount of the average photon number budget that you have. So I'll put a capital N here. And I said it was g of 1 minus lambda n minus g of lambda n. So usually you can't actually compute the quantum capacity because if you remember, there was this formula for the capacity, and it was in terms of this regularization. Where this Q1 is just defined as the maximum coherent information that you can generate. Sorry, I should use H's rather than S's. Where this is now a mixed state input to your channel, and these are just the induced output at the channel and the output in the environment. Remember, any channel I can think of as mapping some input space A according to some unitary to an output space B and an environment, and the action of the channel just applies the unitary and traces out the environment. And we also had this N, this is trace out over E, the channel. And we talked about this N hat, which is just the complementary channel. You trace out B instead. So in general, I mentioned that this thing is not additive, which means there are examples of channels where if I take, say, 2 copies of the channel and evaluate this Q1, it's strictly bigger than twice Q1 of the channel. And that's what makes it difficult to evaluate this limit. We don't really have a good understanding of when this happens and how quickly this limit converges. So it's a difficult thing to evaluate. Nevertheless, I wrote down this formula for the capacity, not just Q1, but Q. And that's because this channel actually has a particular special form called degradability. So I'll just give you a definition and a quick proof that degradable channels have additive coherent information, because I think it's very nice. So what is a degradable channel? A channel N is degradable if there's a second channel, D, such that when I compose the channel N with D, I get the complementary channel. So somehow the output of the channel is strictly stronger than the output of the environment. So I can completely simulate the channel from input to environment by doing some further processing on B. And when a channel is degradable, that means that this coherent information is additive, and indeed the quantum capacity of the channel is just the single letter coherent information. Yes. Like, no, it's Q1 of n. Okay? If I have a degradable channel, Q of n hat is 0. Right? That's similar to yesterday, right? Because I know that this knows strictly less than this person. So if I had a capacity from here to there, it would mean a capacity from here to there, and it would give me cloning. So that's actually related to that gives a test for having 0 quantum capacity. So these degradable channels, and they're complementary channels people call anti-degradable, are two classes that we can compute the capacity for.
So D goes from system B to system E again.
That's right, yeah.
So identity channel is trivially degradable.
Yes. And a dephasing channel is sort of non-trivially degradable. And this is also non-trivially degradable, right? Like, I can just attenuate this even more to get that. Okay, so why does this work? Well, what you have to do is say, well, let's say I have a particular input state. Phi 1, 8, 2, that I evaluate the coherent information on. Okay, now this gives me a rho B1, E1, B2, E2. And what I'd like to show is that the coherent information evaluated on this state, so we assume this is like the optimal state, which is entropy of V1, B2 minus entropy of E1, E2 is less than or equal to the sum of the two coherent informations that I get by just looking at this state, phi A1, A2, and I evaluate one coherent information with respect to A1 and the other with respect to A2. Right? So what do those give? Those actually give entropy of B1 minus entropy of E1. And the other one gives entropy of B2 minus entropy of E2. And the point is, this term is a lower bound for Q1 of a single copy of the channel. This term is also a lower bound for Q1. And since I assumed this was the optimal state, this is going to be equal to Q1 of two copies of the channel. So what we need to do is show that this is less than or equal to the sum of those two. Then we'll have shown that this Q1 is additive, and this limit doesn't need to be included, and I can just evaluate this. So I can just kind of re-express this inequality that we're hoping to prove. Okay, so I should put a big question mark here because it's not proved yet. But what we want to prove is I'm going to put everything with an E on this side and everything with B on this side. We want to show entropy of E1 plus entropy of E2 minus entropy of E1, E2 should be less than or equal to entropy of B1 plus entropy of B2 minus entropy of B1, B2. Okay? And you guys already recognize this, right? What's this on the left?
Mutual information.
Right, it's a mutual information. So mutual information, E1 between E1 and E2. We want to show, we don't know that yet, should be less than or equal to mutual information between B1 and B2. Now, I don't think anyone explicitly stated this property yet, but let's say I have some method of measuring the correlation between two systems. What should happen if I apply some noise to one of the systems? What does that do to the correlation? Decrease, right? It should decrease. And you know, this mutual information has this property that when you degrade one of these systems, it always decreases the mutual information. And the property of degradability tells me exactly that when I apply this degrading map to B1, I can get E1, right? So that means that actually the mutual information between B1 and B2 has to be bigger than the mutual information between E1 and E2. Now we didn't prove it's called the data processing inequality that actually tells you that when you degrade from one system to another, you decrease the mutual information. But it's not difficult to prove, and it's actually something you can do with just strong subadditivity. So that we've looked at a few times this week. So maybe in tutorials it could be fun to prove. I think you use you use strong subadditivity twice, right? Once for each of the degradings that you do. Okay, so that's just a quick comment about why we know what these attenuation channels do. Okay, so now there's we learned a couple of classes of channels. 3 classes of channels I have in mind that we can compute the quantum capacity for. So let's just write them down. Can anyone name one? Entanglement breaking? Yeah. Antidegradable? Another? Degradable, yeah. And actually, this entanglement breaking is a subclass of a different kind of channel called PPT channels, right? So these are channels who only can make PPT states. These things also have 0 quantum capacity. So I'll just say PPT channels. Now, how do you tell if a channel is PPT? You just make one of these 2-mode squeezed states that we talked about, apply the channel to it, half of it, and now that gives you a state rho AB, and just check that that's PPT. And you can translate these conditions for PPT on the state to conditions for PPT on the channel. Remember, there was this X and Y for the channel that have to satisfy this property that Y should be bigger than or equal to, or what is it? I think it's Y plus I J minus X J X transpose. Maybe I messed up the transposes a bit. That should be bigger than or equal to 0. That's the sort of physicality condition for the quantum channel. Oh, that maps gamma to X gamma X transpose plus Y. And if you want the channel to also be PPT, it turns out you just turn this minus sign to a plus. So in order for it to be both PPT and physical, the X and Y better satisfy that. And there are some non-trivial examples of those channels. So how about the quantum capacity for these? We can compute it. It's 0. We can compute these. Those also have 0 quantum capacity. And these actually generally don't have 0 quantum capacity. So this is the only sort of, quote, non-trivial. This is the only sort of channel we can compute a positive capacity for. And it's just given by the single letter coherent information. So there's some fun games you can play with this, actually. We'll leave it this. We'll take that. So one of the things that is kind of fun is you can find examples of channels that have these 0 quantum capacities. So I can find Q1, Q of N1 equal to 0 because it's antidegradable. Antidegradable is just a slightly more general notion than this symmetric channel thing we discussed yesterday. Right? It means that the output has less than, well, that the environment gets at least as much as the output. Symmetry sort of required that the environment and the output got exactly the same thing. And you can find also non-trivial channels that have 0 quantum capacity because they're PPT. And one of the cool things that you can do if you pick these channels right is figure out ways to make this joint quantum capacity, so the capacity of the tensor product of these 2 individual channels, positive. And I don't want to say too much about how to prove this, but in the discrete case, so when you have finite dimensions, one way that you can go about proving this is by using a construction of the Horodetzky family and Jonathan Oppenheim that gives you quantum channels that are PPT, so they have zero quantum capacity, but they have positive private capacity. And this is somehow an important ingredient in demonstrating for these finite dimensional channels that you can have positive joint quantum capacity. Basically, you can show anytime you have positive private capacity, you can turn that into positive quantum capacity by combining the channel with positive private capacity with a symmetric channel. Okay, so
since Q is non-additive,
mhm.
can't I say that N1 and N2 may have a correlation and therefore it will be greater than 0?
Well, if you were allowing correlation, you could easily make it greater than 0.
Yeah.
But these don't have correlation. They're just totally independent. That's why it's unusual that it can be greater than 0. Right? So the independence of the noise might make you think that it should be additive. But the fact that it's not additive suggests that there's some sort of non-trivial way to use the two channels together. Okay, so, oh, yes? I can't hear you.
On the right hand side.
This? No, over here. Okay, this. If the channel is anti-degradable, it has 0 quantum capacity. If it's PPT, it also has 0 quantum capacity. This line. Oh, I'm just saying that I can find examples of such channels when I take the tensor product of them that have non-zero quantum capacity. It's positive. And the point is that if I take two anti-degradable channels and tensor them together, that's still anti-degradable, so it still has 0 quantum capacity. If I take two PPT channels and tensor them together, that's still anti-degradable, so it has 0 quantum capacity. But if I take one of each, it can happen that there's no reason for it to have 0 quantum capacity, and indeed, it can have positive one. So that's just like, it's a non-trivial fact that I'm just mentioning. And I'm not showing you the examples, but I just want to give you a feel for what properties these channels have to give that. Oh, sorry.
Can one classify those channels which will have these superactivation or superactivity?
Not as far as I know. I mean, this is certainly, well, you can have feelings about it, but I don't have any strict classifications or anything like that. Like, you might hope that if this private capacity is equal to 0, then you can't have a superactivation like that. However, we don't really know, well, we don't know how to prove that. And furthermore, we can't really check that because we don't have good examples of channels with 0 private capacity that aren't anti-degradable.
So these winding entanglement channels,
Mm-hmm.
in this state it will produce bound entanglement.
Mm-hmm.
So that is not the only class of channels which will have this property.
No, the other class of channels are the symmetric channels. And you have to take one from each class. Now, symmetric channels don't typically have 0 distillable entanglement associated with their Choi matrix. It's only the one-way capacity that's 0. And actually, if you want to have this happen if you want to have a superactivation of two-way distillable entanglement, you explicitly the only thing you need to do is find NPT bound entanglement. It's sort of equivalent to finding that.
Can you repeat that statement?
If you want to find pairs of quantum states with positive distillable entanglement where each of the individual ones has 0 distillable entanglement, it suffices to, and it's necessary and sufficient to find an NPT state that's not distillable.
Is
Yeah?
there any way we can
Well, it's more than mathematical result. It's related to this fact, that you have quantum capacity 0 but positive private capacity. And from that, you can show this fact. Basically, you get a lower bound of half the private capacity. So there's a specific channel that's symmetric, and you get a lower bound of half the private capacity of channel 1 when you take the joint capacity of channel 1 and this A symmetric channel. Oops. Okay, so I want to continue because there's something kind of nice here that, okay, first of all, I said all of these things, this is for finite dimensions. So what happens for bosonic channels? Okay, we know that there are PPT channels that are non-trivial. So there are these entanglement binding channels for Gaussian states on two modes, actually. They map two modes to two modes. We have this attenuation channel that is 50-50 attenuation. That's also got zero quantum capacity. So you might want to go off and try to find a pair of channels that does this for these Gaussian states, for Gaussian channels. And it turns out you can, although, well, let's say it doesn't. Okay, it turns out you can. Let me just show you what they are. The first one is this 50% attenuation channel. And the second one, I'll just draw a circuit that does it for you. It takes two modes in, has two modes in the environment. It does some passive optics. Then there's a pi phase shift down here. And then there's some squeezings. And then it applies the inverse of this unitary. Okay. Oh, and then these get thrown away. These are the environment, and these are the output modes. So that's how the channel acts. It looks a little complicated, and you might say, where does it come from? And the answer is a computer. And the point is, with all of this stuff, if we're talking about just Gaussian states, I can just write down gammas and start asking questions about what their entropies are. I can constrain them to be the channels to be either PPT or anti-degradable. And I can just look for things that give me a positive coherent information. And then you can try to understand what the channel is doing and extract it, break it down into this structure where you have some orthogonal matrix, some single mode squeezers, and another orthogonal matrix. Now, I want to talk about some open questions. So the first open question here I have is, in the finite dimensional case, the only way I know how to show this result, this positive quantum capacity where I have an entanglement binding channel and an anti-degradable channel, is by taking a channel that has positive private capacity and using this result. In the case of Gaussian states, what I have is some example that I know has zero quantum capacity and is PPT. Well, sorry, this is zero quantum capacity, and I combine it with something that's PPT, and that gives me a positive joint coherent information. So when I evaluate this Q1 on N1 tensor N2, that's positive. But I don't know anything about what the private capacity is. Okay? So specifically, I don't know of any Gaussian channels that are PPT, which means it has zero quantum capacity, but they have positive private capacity. And, well, I don't know. It's so in order to try to figure out whether we can answer this question or find such examples, I think it's good to look back to the discrete case again and ask, what are these classical channels that have positive private capacity and are entanglement binding? So, oh yeah.
This last one, let me just the non-PPT two-mode Gaussian channels. What is the situation? You know that their private capacity is 0, or you don't know their private capacity?
I don't know. I mean, yeah, so I just don't know. I mean,
so therefore, it's potentially possible that the two-mode PPT Gaussian channels have non-zero private capacity.
oh, absolutely, yeah. But I mean,
Okay.
yeah, there's just like, yeah. So, but that's the question. It's like, it's a question about some 4x4 matrices, and what's the answer? I don't know, but I mean, I feel like one should be able to answer that. So, in order to sort of motivate this question or talk about it a little bit, I want to tell you about, and I'm going to switch a little bit between talking about states and channels, but you can always go between states and channels by taking your channel and making a Choi matrix out of it, like this, and then talking about this state. And if this state is PPT, then the channel is PPT. If this state has, or if this channel has positive capacity or positive private capacity, then this channel has one-way distillable entanglement or one-way distillable key. So I apologize, but I'm going to have to go back and forth between these languages a little bit. So let me just give you examples of states that separate distillable entanglement and distillable key, because those are kind of the essence of finding channels that have positive private capacity but 0 quantum capacity. So we're going to let phi plus is just going to be 0, 0, plus 1, 1. And phi minus is going to be 0, 0, minus 1, 1. And I'm going to take phi plus on A and B. Actually, let me write it like this first. And I'm going to tell Bob, B, whether I have a phi plus or a phi minus. So I have a mixture of these two. I'll do it like this. So I have a mixture of a phi plus and a phi minus between A and B. And then I have this little register B that holds plus when it's phi plus and minus when it's phi minus. So quick question, what's the distillable entanglement of such a state? 1 EBIT, right. Why? Because Bob can just figure out whether he's got a plus or a minus and appropriately either correct or not correct this phase error, right? So you can just get an EBIT out of this. And in a similar way, I could have given this plus and minus state to Alice. But now I'm going to complicate the situation a little bit. And this relates also to what Fernando talked about a bit. I'm going to flag these guys with tau plus on little a, little b, and tau minus on little a, little b. So now these, I think, well, they should be, if they're orthogonal, that's great. That means, well, that makes you feel like you should be able to still distill out a full p-bit, or full e-bit, right? Because you should be,
Tau plus and tau minus are pure states?
they'll be mixed states, right? But for now, think of them as orthogonal. So if they're orthogonal, we should be able to play the same game up here. Just figure out which state you've got, tau plus or tau minus, and apply the correct, correct phase correction.
They may not be locally orthogonal, right?
Right, so I just mean this. So yeah, the supports are orthogonal. Okay, so I heard someone bringing up the right point, which is actually they might not be locally orthogonal. And Fernando mentioned these data hiding states, right, which are orthogonal. However, if you try to distinguish them via LOCC, you do a really bad job distinguishing them. Okay? So at least in this case, this strategy is not going to do a very good job of trying to get an E-bit out. And it turns out, well, you can do a few things, but one of the things you can do is take just examples of data hiding states, like things that are related to the projector onto symmetric and antisymmetric space, which are going to be orthogonal, and just plug them in here and compute some entanglement measures of this. So you can get an upper bound on the distillable entanglement of this, and you can show if you let these dimensions grow, the distillable entanglement of this thing is going to get small. And that means the channel associated with it via this mapping is going to have small quantum capacity. Okay? So we can show that this is going to have small distillable entanglement and small quantum capacity. I mean, that's not a proof, that's just an intuition, but you can either evaluate some... Oh, well, the intuition is just that the best thing most people can think of doing is just trying to distinguish tau plus and tau minus. You can't do that very well locally. And if you can't do that very well locally, this information about whether it's a phi plus or a phi minus is not very useful to you. If you don't know whether it's a phi minus or a phi plus, right, if you just trace out these flags, this is a totally separable state. Right? So if I just trace out the flags and just have a perfect mixture of phi plus and phi minus, I just get the state 0, 0, tensor 0, 0, plus 1, 1, tensor 1, 1. So what we're doing by mixing these things together is causing quite some problem unless we know which state we've got. But if we take that information about which state we've got and delocalize it in a way that they can't access it, it makes it very hard for them to get distillable entanglement. Now, to make that precise, you can just evaluate some entanglement measures for this, like a relative entropy of entanglement. Another thing you can do is add some noise to it, like mix in another state. And if you mix in a little bit of another state, you can make this a PPT state. So these states have small quantum capacity, but actually this state is very good for generating a perfectly secure secret bit. Why is that? Well, why don't I just tell you the protocol that they're going to use to extract a secret bit. Alice and Bob both just measure in the computational basis, the sort of standard basis in which I've written phi plus and phi minus. So why is that going to be secure? Well, let me write it in this way. Let's suppose I start with just a phi plus AB. And then Alice and Bob measure in the computational basis. Well, if I start with a phi plus AB, and Alice and Bob measure in a computational basis, they have perfectly secure key. There's not even an environment around here. So maybe just I should write some sigma E. Any measurement outcomes here in this computational basis are going to be independent of the values of outcomes on the environment. Yeah, yeah. So it'll be perfectly it'll agree exactly, and furthermore, nobody's going to know about what those outcomes are. But now, if I throw in a little bit of extra stuff for them to hold on to, some little a and little b, and some mixed and some environment that purifies little a and little b. Still, it's going to be totally secure. If they measure this in the computational basis, they'll get some key bits that are uncorrelated with this E. Now, what if I start with such a state, and then I apply a controlled rotation, right? I apply a controlled rotation from the B side to the AB system. That's actually going to make a state just like this, right? You can think of this, the minus on this phi minus, as being generated by some phase kickback from a controlled rotation on this tau plus, tau minus space. Okay? So that's exactly how I can make this kind of state. But the point is, that rotation that I'm talking about doing totally commutes with the measurements that I was talking about doing. So if it commutes with the measurements, the security of the key isn't going to be compromised because the statistics of the relationship between the AB system and the E system are the same in both cases, as long as Alice and Bob are actually holding on to these little registers that they call the shield system. So that's the intuition for why this kind of gives you something that has higher private key than it has distillable entanglement, and that gives you a quantum state that has, a quantum channel that has higher quantum private capacity than it has quantum capacity. So this is the kind of construction you can use to generate these kind of examples to give you a superactivation like that. Now, I don't know how any of this translates into Gaussian language, but it would be very nice. Like one slight hint that maybe it would is the same, one of the consequences of it working does seem to work out. You have a PPT state that has positive joint capacity with this symmetric. That's a little bit like, well, if you want to make that happen classically or in a discrete variables, one way to do that is by using these private states with no quantum capacity. So this, I think it's a really interesting question here, which is, do you have Gaussian states? With a distillable key. Which I haven't defined, but the point is it's just like distillable entanglement, but now what you want to do is distill classical correlations that are uncorrelated with the environment of the state. Or put another way, are there Gaussian PPT channels with quantum capacity equal to 0, but, well, those of course there will be, but private capacity that's positive. And again, it seems like the kind of question you could attack by looking at just covariance matrices and evaluating mutual informations and stuff. We have some lower bounds for this private capacity in terms of differences of mutual informations. We know how to evaluate mutual informations of Gaussian states, so maybe one could find such things. Of course, there's another issue, which is we talked about these data hiding states. I can take two orthogonal states, or approximately orthogonal states, that are bipartite, and via LOCC are very hard to distinguish. Okay? Again, that's sort of a really useful kind of tool to be able to talk about, to be able to build quantum states like these, but to think about other different kinds of protocols. And we don't know whether that kind of thing happens for Gaussian states either. Right? So, is there some notion of Gaussian data hiding states? And I'm not sure what I mean by that. I might mean, can you find pairs of states that are globally fairly distinguishable but locally hard to distinguish, or hard to distinguish even by LOCC? Or it might mean, can you find a parametrized family of states that hides an entire quadrature? Either one of those, I think, would be pretty interesting to understand, but I'm not really sure how to go about attacking it. Again, it seems like something that you you could start asking questions about, because we know about the kinds of measurements you can do on Gaussian states, and we have compact ways of describing them. So it's I think, an interesting question to look into. And once you find them, of course, then you can go and maybe try to answer this question by using them in a similar way to the way you use the data hiding states for this construction of PPT states with distillable key. Oh, something else that I thought might be interesting. So we know in the case of in the discrete variable case, we have simple examples where this coherent information is non-additive. Oh, whoops. So for example, well, it's not quite true, but if I take 3 copies for, say, a depolarizing channel on qubits, then for certain values of error probability, I can find that when I evaluate the coherent information on 3 copies of the channel, it's just strictly bigger than 3 times the coherent information on 1 copy of the channel. Now, I don't know of any examples of channels of Gaussian channels where I get this kind of non-additive coherent information, actually. I do know of examples of pairs of channels where the coherent information of n1 tensor n2 is bigger than the sum of the individual channels. And in finite dimensions, there's a simple way to turn that into an example of a single channel that gives you this kind of non-additivity of coherent information on a single channel. But I don't know how to take those 2 Gaussian channels and combine them in a way that gives you a Gaussian channel that has this property. I would guess personally that just the simple phase covariant channels we talked about a few days ago with just thermal noise channels would give this kind of non-additivity, just kind of based on the analogy with the depolarizing channels in qubits. They're sort of very symmetric, but they add this kind of extra noise that's very different from the information the environment has. But we don't know. So I think this is also kind of interesting.
You gave that example of qubit depolarizing channel. Why do you go from 2 copies to 3?
Oh, because if you do it on 2 copies, I just know that it is actually additive. I mean, yeah, that's right. So I'm hesitating a little bit because I, quote, know that because I've done a lot of numerics on it. So, I couldn't prove it. I just know that if you go to 3 copies, it's actually pretty easy. So, and in 2 copies, you can pound on it and you won't see anything. So, that's why I said 3. Pardon?
More than 3 copies.
Uh-huh.
More than 3 channels. Is it greater than 4 n kind of Q of n cross n cross n? Cross n.
Yep.
4 of them. Is it greater than 4 of Q n?
Yes.
It is.
Well,
This is the general result. That's what
oh, well, in general, we always know this. Is greater than or equal to n times q1 of n. What's interesting is finding the cases where it's strictly bigger. And it's not always strictly bigger, but you have to work to find cases where it's strictly bigger. And generally, it tends to be in a regime where things are very noisy. So this is not true for sort of every channel or for even every parameter value of a depolarizing channel, but only when it's very noisy. Oh.
So is it always true that if you add noise
Mhm.
channel, then the difference between the left hand side and right hand side, the inequality, it will increase?
No, it's not always true, because if you add enough noise, you make it like a completely trivial channel that's just completely depolarizing, and then the difference is 0 again. But it is sort of a general rule that this difference, as you're adding noise, well, this is all just sort of intuition and looking at examples, but the cases I know of is when this Q1 starts to get close to 0, then you start to see this getting to be a little bit bigger than that.
I think generally it will not be true, because if there is no noise, certain things will be additive.
Yep.
If there is too much noise, it will be trivially additive because everything becomes 0.
Yeah.
Therefore, as Dirac would have said, there's an optimal distance at which girl is most beautiful. So maybe there is an intermediate noise where it is violation is maximum.
Right, I think it's true. Although it tends to be quite high noise, at least if you want to show something. If you want to give an example, we always tend to see things where it's quite high noise in terms of how big this Q1 is. Okay, this was sort of, I guess I sort of mentioned a collection of questions that I thought were interesting about Gaussian channels here. Now, I wanted to talk a little, oh, please.
In that case, you are saying that for 3 copy quantum capacity is non LC.
Yep.
So in of that channel, what about the private? Suppose I show that for some channel, quantum capacity is non LC.
Mm-hmm.
Is it follows that private capacity must be non-additive, maybe additive?
It could be additive, but the way I would bet is that it will probably also be non-additive. Just again, based on some examples that we understand. And for that particular channel, it is also non-additive. Yeah.
It's cubic depolarizing channel.
Mhm.
Anything is known about cubics, kind of cubic, let's say?
Um,
No, I'm just asking.
No, I mean, well, not by me, and I would say probably I don't think anything's known. This is, I mean, well, no, that would be worth looking at. Although, well, this is simpler than a qubit than QDIT, and if you want to do numerics, already this is kind of hard. Because when you try to do this, when you try to evaluate this Q1, this optimization can be quite difficult. It's not like a convex thing or something. So if you want to evaluate this on 5 copies of the channel, you can find an answer. But if you want to do it on 10 copies of the channel, you will not find an answer.
But this result itself is not numeric.
The result here, no, it's not. But one of the things you can do to try to understand it is optimize things a little better. What you do is you take a particular channel that inputs this and evaluate this difference of entropy of B and difference of entropy of E, and difference of entropy of B and E, and you just look at it, and it's positive. Oh.
The other question, in the past construction of Oppenheimer used to say that quantum capacity of N1 is 0 and N2 is 0, that tensor product quantum capacity greater than 0. And for this, private capacity of N2 must be positive. But
Yeah.
what about private capacity of N1? It may be 0.
In fact, it is a 0 in these cases because it's a symmetric channel.
At least one must have positive private capacity.
For that construction to work. But
But it is not required, not necessary.
not as far as I know. And probably not, because you can find examples with very small private capacity and big joint quantum capacity. But I should emphasize that if you want to find a channel that has 0 private capacity, and you want something other than anti-degradable channels, it's very tough. I mean, there are no examples, basically. Okay, so I thought I would also talk about another topic that I guess is going to require just a little bit of background first. But if you guys want to ask more questions or think about this a little more, we can certainly do that first. Or we can talk about it later. It's okay. So now I'll just erase this. So now I want to talk about, let's see how to start this. Okay, so let's just talk about classical random variables on just real random variables. No, we're going to start with quantum, okay? So let's say I take some quantum state rho A, it's a bosonic state, and I take rho B, it's also bosonic, and I have some beam splitter with transmissivity lambda again. And I sort of mix these two things on the beam splitter or combine them at the beam splitter, and then just look at this system C. The question is, what is the relationship between the entropy of C and the entropy of these two? If I was mixing these two together, literally taking the mixture of these two density matrices, we would know that 1 minus lambda of rho A plus lambda of rho B, that was the density matrix, and the entropy of that is bigger than or equal to 1 minus lambda entropy of A plus lambda entropy of B. So there's a classical result about classical random variables that tells me when I do something similar, namely if I take A, X, and Y, and I map them to square root of 1 minus lambda X plus square root of lambda Y, and I call that Z, the entropy of Z is bigger than or equal to the corresponding average of the entropy of X and the entropy of Y. And I'm sorry, I'm sort of, I'm trying to be consistent by calling the entropy H everywhere, but sometimes I forget and call it S. I forget which way people usually do it. I know physicists and information theorists each have their own convention, but I don't remember which is which.
I think physicists tend to use S for quantum and H for classical.
Oh, okay, okay. So,
So that's why I was always amazed when you explicitly take a quantum thing and then after writing S,
You change it to H?
And change it to H.
sorry, I mean,
It's all right, but
just by context, right? If it's a quantum state, we should use von Neumann.
the
But
last 4 days we have learned to live it.
okay. Okay. So the point here is that I haven't taken just a mixture of, well, the point here is that this is a sum of the two variables. That's not the same as mixing the two probability distributions together. Actually, it's like taking the convolution of the two probability distributions when you add them. So it's kind of funny that when you add them, the distributions in this different way, that you still get something that looks like a kind of concavity for entropy. And it turns out that you can prove for arbitrary quantum states an analog of this thing, specifically if you take rho A and rho B and knock them off beam splitters and look at the entropy of C, a lower bound for the entropy of C is just the average of the individual entropies again. And let's see. This is actually kind of a useful inequality for in information theory, this thing. It's called the entropy power inequality. And it has several equivalent forms that well, no, I won't write. It has several equivalent forms. I guess the standard way that people write it, or the first way that people wrote it, was e to the 2 entropy of z over n, where this is z lives in Rn, should be bigger than or equal to the average of the individual values, 1 minus lambda e to the 2 Okay, so that's one way you can write it. You can also write it without these lambdas if you remove the lambdas here, but that's hard to generalize to the quantum case. So we're always going to talk about, in the classical case, stuff that preserves the average variance. Okay, so the analog of this for
On the right hand side, it is multiplication or addition?
this is addition. Yeah. Equality that you can show about this, about the entropy at C. The reason that it's nice, besides it has applications to information theory, is that it tells you, usually you think of when I mix things together, literally add the two density matrices together, that increases the entropy. What this tells you is that when I combine these things at a beam splitter and get rid of the other output of the beam splitter, I'm also going to be increasing the entropy. And furthermore, since we're talking about bosonic states, and this operation preserves the average energy of these two states, this is telling me that as I do this process, as I start combining states together, according to this process, I'm increasing the entropy. We know that the state that optimizes the entropy is Gaussian. So it's now also telling me something like the fact that if I start with two different states and I knock them off a beam splitter, that I've made the state more Gaussian in some sense, in some quantifiable sense. And if you imagine doing this over and over again, it can give you some non-commutative version of a central limit theorem. Okay, so this is one result that I know how to prove for arbitrary quantum states. There's another that I can show you. It's a little bit like this, but slightly different. And I actually only know how to prove this for lambda equals a half. It's kind of a similar proof technique to the one for this, but it only seems to work for a half. And then there's a third thing. Well, first of all, I'd like to be able to prove this for lambda's not a half. But there's this third inequality, which is really not proven, but would be beautiful, and specifically it would imply the additivity of the minimum output entropy of these channels we were talking about on Wednesday. It's called the entropy photon number inequality. And here I just replace this exponent with a G inverse. I'll remind you in a second what G is. And G, remember, was just the thing that took the average photon number of a thermal state and mapped it into the entropy of that thermal state. So you can see what I'm trying to do when I apply a G inverse to an entropy is figure out what's the average photon number that a thermal state with this entropy would have to have. Okay, so this would be really cool. We don't know how to prove it. This I know how to prove for lambda arbitrary. This only for lambda equal to a half. The methods here are reasonably complicated, and the annoying thing to me is that I don't. So I know this is true, which means I know this is true for Gaussian states, right? And I know the right way to deal with Gaussian states. The right way to deal with Gaussian states is to deal with their covariance matrices and find symplectic eigenvalues, et cetera, et cetera. However, the only way I know how to prove this for Gaussian states even is to go through the entire machinery that I know how to use for the arbitrary quantum states. And that seems annoying. This is just a statement about the symplectic eigenvalues of G. all here. I should have replaced this. This is certainly true when I mix the two states together, but it's also true when I, quote, mix them on this beam splitter. So this should be written like this. This should be just C. So now this is a statement about the symplectic eigenvalues of A, B, and C, and specifically if I have some gamma A and some gamma B, and I mix them on a beam splitter like this, with transmissivity lambda, the output of this single output of this beam splitter is going to have covariance matrix 1 minus lambda gamma A plus lambda gamma B. I'll call that gamma C. No, I'll just leave it and call it that. Okay, and then we know there's a nice formula for the entropy of a Gaussian state with a given covariance matrix, right? I figure out the symplectic eigenvalues. I add up over the different symplectic eigenvalues, g of the symplectic eigenvalue minus 1 over 2, and that gives me the entropy, which I'll just call entropy of, sorry, it's, okay, now I'm self-conscious about it. Okay, so entropy of that, I'll just call this expression the entropy of this covariance matrix. So then we know that
On the right-hand side, when you say covariance matrix, the Gaussian state with that covariance matrix.
yeah, but I just want to use, well, right, it's a different function. The argument is a covariance matrix. Then to compute it, you go off and find the state and find its entropy. So then this tells us then something about this function on covariance matrices. Right? It tells us that 1 minus lambda times the entropy associated with the covariance matrix gamma A times entropy associated with the covariance matrix gamma B is a lower bound for entropy of the average covariance matrix. Okay, and since this is just a statement about covariance matrices and their symplectic eigenvalues, I would rather be able to prove this without going through all the machinery necessary to describe infinite dimensional systems. I'd like it to be just some matrix inequality that we can prove.
If I understand this statement right, so you have some proof on that first equation at the top.
Yep.
But that using other machinery.
Yep.
And you would like it to be proved directly using properties of the independence of entropy on the symplectic eigenvalues.
Yeah. And even better, I would like to prove this one, and then prove it for arbitrary lambda, and then prove this one for arbitrary lambda too, because I don't even know how to prove. I don't know how to prove this for Gaussian states. Now, for a single mode, there's a proof for this. Actually, based on some of this, you can do it based on some of the stuff we discussed yesterday. But some other people already showed it when they're trying to study this, that for single mode Gaussian states, this is satisfied. But in general, I think it's a really nice collection of questions. Now, remember what this, if we think about what this means, right? This entropy of C, if C is a Gaussian state, then let's look at what this conjectured inequality says. And let me just change it a little bit. I have to divide everybody by the number of modes. Okay? So then we can ask, what does this, I'm going to use some bad notation again, and I'm just going to call I won't use it. Yeah. So I'm just going to call, gamma of C is going to be equal to 1 minus lambda gamma of A plus lambda gamma of B. Okay, and I'll call the symplectic eigenvalues of this gamma sub I C. And basically, all of these inequalities are about the relationships between this guy's symplectic eigenvalues and these symplectic eigenvalues. Okay? So gamma of C are the symplectic eigenvalues of this. These are the gamma of A, or nu of A. And these nu of B are symplectic eigenvalues of this guy. Okay, so what's entropy of C? It's just sum over I of G of nu C of I. And entropy of B is sum over I G of nu B of I. And similarly for entropy of A. And then you can see, let's look at what this inequality would mean. Well, in the single mode case, it's pretty simple, right? Because this has no sum, and for one mode, this is just G of mu C. And then we have G of mu A and G of mu B. And then the conjectured inequality is just going to apply a G inverse on these guys. So it just says, well, what we should have is nu C is bigger than or equal to mu A, the average of mu A and mu B. And actually, this turns out to be, this is just true. Now, the inequality basically, here, again, if we start thinking about what's going on, this H of C over N is just the average entropy over all the modes of, each of the, basically it's the average, how do I put it? Well, that thing has, that inequality has a 1 over N in it. So we'll get rid of the one mode stuff. So all of these inequalities look like this. So the arguments to those G inverses are just the average entropy in one of the modes in the thermal state that's given by this sort of canonical decomposition of your Gaussian state. So you take the average entropy and then you invert it to find something like the average photon number associated with that average entropy. And this inequality just suggests that that average photon number at the output here should be bigger than the average of the corresponding average photon numbers of the individual components you put in. So again, I don't know, I think it's kind of a compelling idea, and the fact that we know this is true, and it's just a statement about covariance matrices, and I don't know how to prove it except, with only using some symplectic stuff. I only know how to prove it by going through the full Hilbert space, I think is a very interesting open question. So all three of these inequalities would be cool to show through some sort of matrix stuff rather than a whole bunch of quantum mechanics. And actually, I didn't say much about how you prove these, but I don't think I will. I'll just say that I'd rather be able to do this in a simple.
That proof is available somewhere?
Yeah, it's on the archive. It's just sort of a longish paper, and I'd have to introduce a lot of notation by the time.
One of the people referred to in the abstract.
Oh, okay.
Obviously, I have not read
Is it?
1205? Your paper was Robert?
Yes, that's right. Okay.
No, you didn't probably. I think Andreas did all that job for you.
I put in some random references.
I actually wrote the abstract, but I didn't put in any references.
Yeah, of course.
Okay.
So he did the job for you.
Okay.
Or for
Thanks.
us, whichever way you look at it.
Okay, so I think at this point I'll stop. Thank you. Thank you for having me.